Okay, hi everyone. Welcome to the theory session, which is the penultimate session here at POPL. And I think we can just go ahead and get started. So our first talk today will be by Vikraman Choudhury, who's going to tell us about the duality of lambda abstraction.
Hello. Hi, I'm Vikraman from the University of Bologna. I'll tell you some nice ideas about how the lambda calculus can be dualized. I personally think it's very beautiful. I'll try to convince you in 17 minutes to look at my paper. So I'll start with a very simple puzzle. We've been thinking about the lambda calculus for a long time. It's a theory of higher order functions. So if you take your favorite typed functional programming language, you can implement curry and uncurry, right? So what curry does is you have products on the left, and it gives you a higher order function on the right, and you can go forwards or backwards. But can you dualize currying? Okay. So what does it mean to dualize currying? We know products are dual to sums, so let's put sums on the right. And now I want something on the left which is dual to functions. Okay. So what's a dual to functions? And can you actually get it in a functional programming language? Okay. So it's an interesting puzzle, but the answer is very boring because if you have both currying and co-currying, your language becomes degenerate, which means you can't compute anything with it. So let me give you a simple argument or a sketch of the argument about how this works. So if you have the empty type, the product type, the function, and the co-function, you have one unique way of going from 0 times a to 0, okay, by currying. And if you want to go the other way, there is one unique way of going from 0 to 0 times a, because going into a product means going into both sides of the product. And from this, you can show that 0 times a is isomorphic to 0. Dually, if you have co-currying, there is only one function from 1 to a plus 1, and a plus 1 to 1. So dually, you just get a plus 1 is isomorphic to 1. Okay. Now, if a plus 1 is a times 0 equals 0 is completely fine. That matches our intuition with the empty type. But if a plus 1 is equal to 1, then you'd have 1 plus 1 equals 1, which means you can't have Booleans because you want true and false to be two different programs, right? So this is a technical argument in category theory, which is known as Joyal's lemma. If you have both a Cartesian closed structure and a co-Cartesian co-closed structure on the same category, it degenerates to a preorder, or in particular, it becomes a Boolean algebra, okay? So why am I telling you about this puzzle? Because in 2022, I was reading Girard's book about classical linear logic and why Girard was thinking about all these things. And one of the main arguments about classical linear logic is you can't have duals to functions. So Girard argues that actually you should start from linear logic, where all the connectives are linear, and find a way to dualize everything. So if you have classical linear logic, you have complete duality with tensors and cotensors, and every type has a dual. Okay, in this talk, I'm going to show you a language which has both currying and co-currying, but it's not classical linear logic. It's almost like classical linear logic, but the only restriction that I'm going to put on the language is that it's call by value, okay? And this is not just a simple solution to the puzzle, but when you do it like this, you realize that actually there is a deep insight between co-currying and classical logic and control operators like call CC, okay? And why is this interesting to a programming language audience is because if you do it like this, you get a very nice programming abstraction. I think it's nice. I'll tell you about it. So let me tell you what the trick is. So you want co-curry to take C to a plus b, but instead of c to a plus b, I'm going to double negate the sum, okay? So I'll write c to a plus b to r. When you do this, you can look at the continuation for the sum, which is a plus b to r. You split it into two continuations. One takes a continuation a to r, and the other is b to r. Then you apply currying and move the left continuation to the left and the right continuation to the right, and put the b back inside a double negation, okay? So that's the whole trick, and this is the only thing you have to remember to understand the rest of the paper. But if you actually write down this isomorphism in your programming language, like ML or Haskell, you can do a bit of hacking with two continuations for the left and the right. And this is what the program looks like for co-curry and co-uncurry. OK, so this is a very nice program, but I want to abstract away from it. OK, so the first thing I want to write is these double negations are, in fact, a continuation monad or the double negation monad. So I write Ka to be A to R. And the dual to the function type is going to have a value for B and a continuation for A. And then you look at the type signatures for co-curry and co-uncurry, and there's a K in the codomain of these functions. Okay, and you can do the same thing for curry, where you insert a K into the codomain for the function. So the whole trick is you have curry, uncurry, co-curry, and co-uncurry, as long as you insert some double negations in the right places. Okay. Okay. So this is a nice trick, but I'm a category theorist. I like to understand things from a deeper perspective. So I won't tell you the full details, but you can read the paper to find out what exactly it is. So the trick is really about Kleisli categories. So the continuation monad is a strong monad, and it has a Kleisli category. And when you have a strong monad, you can have a nice, well-behaved notion of weak exponentials. And the Kleisli category for the continuation monad has some additional structure, which is really interesting. It allows you to construct left adjoints to sums. Okay? And the whole premise of the paper is to take these two adjunctions and understand the duality of lambda abstraction. Okay, I will not explain what the trick is here, but we can talk more about it offline. I can tell you lots of interesting facts about negations and adjunctions. Okay, so I'll introduce this calculus, which I called the lambda bar calculus. So it has lambdas and co-lambdas. So the first two rules are the usual lambda calculus rules. Okay. And the second rules, the second row has two other rules which are dual to lambda introduction and lambda elimination. So what the difference is between the rules is that lambda binds a value and lambda bar binds a co-value. Lambda application eliminates functions, and co-lambda coapplication eliminates co-functions. Okay, now you might be a bit surprised, why is there a sum type here? Okay, it's an A plus B. Okay, so let's try to give a logical reading of these typing rules. So, so the lambda bar introduction rule assumes something which is of type A dual, which means A is not true, and it tries to prove B, assuming A is not true. So this is a weird kind of sum where you're not proving directly B, but in a weaker context where you assume A is not true, okay? So this is different from an intuitionistic sum because you don't know whether A is true or B is true because there is an additional assumption like A must not be true, right? So when you look at the type of the co-lambda, lambda bar x dot e, it has a type A plus B, but this type A plus B behaves like a classical sum. Okay, and the dual to this is the application rule, the co-application rule. So if you have A plus B, and you know A is not true because you can prove A dual, then you cancel out the A and you get a B. Okay, so this is how the typing rules work. And I'll show you some interesting programs you can write using these two typing rules, okay? So when you have functions, you have lambda x dot x, which is the identity function. When you have co-functions, you can write lambda bar x dot x, and the type of this is A plus A dual, okay? When you have functions, you can evaluate them. When you have co-functions, you can co-evaluate them. When you have functions, you can do uneval, and with co-functions, you can do co-uneval. You can compose functions, you can co-compose functions. There's a very nice algebra to these co-functions. And you notice that I'm writing minus because when you look at the typing rules, it behaves like a minus because B plus A minus B gives you A. Okay? So this minus is the dual to the formal dual to the function type. It's like a subtraction operation. Okay, and with these typing rules, you can also make values and co-values interact. Okay, so we've already seen the excluded middle, which is lambda bar x dot x. If you have A and A dual, that's like A minus A. And then you can lift the A to the left and co-apply an A dual, which allows you to prove anything of type B. If you know about call CC in SML, so A dual to A, it takes an argument f of type A dual to A and gives you an A. So you can derive call CC by writing lambda bar x dot f of x, which gives you a plus a. And then you collapse both sides of the sum by doing a pattern match using case. Okay? If you want to prove Peirce's law, it's the same kind of thing. You always have to collapse both sides of the sum. And you can show that you can get all the axioms of a Boolean algebra and all the classical control operators using just these typing rules. Okay? Okay, and now how do you run these programs? So the lambda bar is dual to lambda. So lambdas have substitution, so you get beta eta rules. Lambda bar also has substitution, you get beta eta rules. Because the language is call by value, I have to restrict the substitution to values. But the lambda bar operator has a strong eta rule, which is lambda bar x dot e co-applied to x. Okay, so this is the binding. These are the equations for binding. But there's also something more in this calculus, which is how the intuitionistic sums interact with classical sums. So because both of them have the same sum type, so you see there are three different ways to introduce sums, right? You can either introduce them intuitionistically using left and right, or you can use a lambda bar, which is the co-function. And you can eliminate sums either using case or by co-applying. Okay, so for every pair of interactions, there's a control effect. Okay, so what happens if you introduce an intuitionistic value and then try to eliminate using a co-application? So let me give you two equations. So lambda bar k of type A dual, it's assuming A is not true, right? And then inside the body of the co-function, you say, actually, I know that B is true, so I can just do in right. And then, just forget the lambda bar, and it just goes back to in right outside. Okay. And what if you do the other thing? So you assume A bar is not true, but inside the body of your co-function, you realize actually A is true. And then it's going to jump out and backtrack to the outside. And during that jumping effect, it's going to forget the evaluation context. Okay? And then there's another way of interaction. So if you introduce something classically and try to, so you have a lambda bar x dot v, where v is a value, and then you're trying to observe it with a case. And then the case is going to start executing the right-hand side of the branch and push it to the body of the co-lambda. Okay, so these are the three equations that are very important. And then there are other eta laws that you have to make the language complete. So let me try to give you a very classic example of a program which was in the original call CC papers. So you're trying to multiply a bunch of numbers in a list. You write your simple ML program, but then there's a 0 in the middle of the list. So you do a bunch of vacuous multiplications with 0. So it's a very long list. It takes a long time, right? Okay. Now you can short circuit this computation and just say in your pattern match that if it's a 0, just don't do multiplication anymore. But that's not good enough, right? Because it's still going to do multiplication on the right of the 0. Okay, now if you have intuitionistic sums, you can actually say, okay, it's an exception, right? So if I have a 0, I'm going to move to the left. So you say int plus int, but if it's a 0, you do in left 0. And if it's otherwise, you just keep mapping things on the right. Okay, and I'm adding a trace function here. The trace is right to left in the style of SML, so it's going to evaluate x and then print the statement. Okay, so if you call this multiplication function now with 0, 3, 4. It's not going to perform any multiplications, but at every step, the evaluation context of the print is going to be executed, so it's going to print at 2, at 1. Okay. Now, these are intuitionistic sums, but now you can rewrite them using classical sums. So it's the same program. Now it has a sum type, but I'm going to do a co-function, and it's the same program, except when you look at the 0, you do the co-application on the left. So in left 0, co-applied to k. Okay, and when it reaches the 0, it's actually going to jump out by discarding the print evaluation context, and you don't see any trace. So this is how classical sums are, give you more expressive power than intuitionistic sums. So let me just, so there's a lot more in the paper. I'll just summarize a few different things. So these CPS translations, there are different kinds of them, But there's a very nice categorical structure behind them using these duals to function types. And in the paper, this is all explored in more detail. And one nice thing I like about this point of view is you can take all the classical results about the lambda calculus and dualize them very formally. So you can dualize functional completeness, you can dualize arrow languages. And this whole coexponentials and the lambda bar gives you the Curry-Howard correspondence for classical logic. And you can actually give an axiomatization of all the control effects using these classical sums rather than the empty type. Okay, so if you go through the paper, I explain how you can recover all the original axiomatizations of call CC or call by value lambda mu. Okay, and I also enjoy programming with co-currying and co-lambdas. So if you look at the types of co-lambdas, it's like a generalized call CC, which doesn't collapse both sides of the sum. Okay, and they are equally expressive, so you can derive call CC using co-lambdas. You can use call CC to derive co-lambdas and the other way. But call CC kind of captures the whole stack, but co-lambdas capture part of the stack. And I have written many programs using co-lambdas, and I really like them when I do backtracking, when you have two continuations. So there's a SAT solver, there's tree search, and I've also implemented a library for effect handlers. You can also play around with this calculus using my interpreter, which is on my on the artifact, and you can implement them in various languages you like. So just to conclude, what's the point of all this? I think continuations are a very well-studied topic, and there's obviously a lot of literature on this. All I'm saying here is a different perspective on continuations and the logical foundations using classical logic. And I really like thinking about classical logic as a computational effect on top of intuitionistic logic, because it changes the way sums work. And I like this point of view of backtracking that classical logic gives you. So I'm happy to tell you more offline about co-lambdas, but if you're teaching your students continuations, maybe you'll tell them about co-lambdas, or if you are programming, maybe you'll think about co-lambdas instead of call CC. There's a lot more to understand about these things. I think this point of view of classical sums and their proof theory, and yeah, I'm thinking about a bunch of these things. Yeah, all right, I'll stop here. Yeah. Okay.
All right, so we have time for a few questions. So does anyone want to start? Raise your hands if you would. Can you get to Bob?
Thanks for a great talk. I just had a slight question. I didn't quite see where you got forced to call by value. I know that you must.
Yes.
I don't disagree with that. I didn't see the spot.
I didn't show all the equations, but here's the lambdas.
As call by value, but I was wondering, like, the point at which you feel forced to do that.
Yes. I mean, semantically, you mean? You mean semantically? Why is it called?
Yeah, like where somewhere.
Yes. It's just because.
Opening example must come into play.
Yes. So there's this thing where I'm working in a Kleiselier junction, and the exponentials are really called by value exponentials because there's a monad hidden inside. Yes. Yes.
And then I think the other thing that's fun to do, which you could do, is you write down excluded middle.
Yes.
And then you'll see that it's a computation and not a value.
Yes.
Whereas all the intuitionistically valid things come down to values.
Yes.
Okay, we have time for another question. Yeah, right over here.
We know classically how to convert lambda abstractions into combinators.
Yes.
Have you got a combinatory account of co-lambdas?
I don't know. I don't know of such a thing. I'm thinking about it. Yes. Yes.
Okay. Let's all thank Vikraman, and could the next speaker come up?